Greetings. This is Tracking Pandemics, Module 1.2, a short history of epidemiology. Epidemiology, as you recall from last slide deck, is the study of patterns of disease. It has its initial roots as far back as 2,500 years ago, with Hippocrates, born in Greece. Hippocrates was largely considered the father of medicine. He established medicine as its own discipline. In 400 BC, he wrote On Airs, Waters, and Places, which begins, "Whoever wishes to investigate medicine properly should proceed thus. In the first place, consider the seasons of the year and what effects each of them produces, for they are not at all alike." He continues on in this vein, proposing a rational approach to explain the occurrence of disease. This was a radical departure from the thinking of the time, which proposed supernatural reasons for disease. Hippocrates suggested environment and host factors, host behaviors, are ultimately responsible for the spread of disease. We fast forward many centuries to a gentleman named John Graunt, lived in the 17th century. Graunt was a retail salesman by trade and largely regarded as the founder of a field called demography, which is the statistical study of human populations. In 1662, he published a landmark analysis of mortality data using the Bills of Mortality. These are weekly publications in London on births, deaths, and causes of death. John Graunt's first publication to quantify the patterns of birth, death, and disease occurrence and noted disparities in these numbers between males and females, noted high infant mortality, differences between urban and rural populations, and variations between seasons. These are some of the first quantifications of patterns of birth, death, and disease. Also important, he critiqued the method of data collection for the bills of mortality, particularly how they noted the causes of death, and suggested plague was mistakenly overrepresented. We see this same kind of critical analysis of methods applied to infectious disease even today. One great example from the recent past is HIV. Generally with HIV, patients die from some secondary infection as the direct cause. And for many years it was difficult to assign HIV as the cause of death. Cholera in 19th century London proved an important historical period for epidemiology and the study of infectious disease. To frame this, we'll look in particular at three men at the center of the London cholera epidemics. The first is William Farr. William Farr built upon John Graunt's work by systematically collecting and analyzing Britain's mortality statistics. Farr is considered the father of modern vital statistics and surveillance, and he developed many of the basic practices that we use today in disease classification. Farr concentrated his efforts on collecting vital statistics, assembling and evaluating those data, and then reporting the results to responsible health authorities and the general public. This was important because it established a framework for using data to determine the impact of underlying conditions on mortality and morbidity, conditions such as living conditions, age, etc. William Farr used these conclusions to push for reform, particularly in sanitation, as a way to combat infectious disease. We'll come back to that in a slide or two. In the 1700s, Great Britain was beginning to transform into an industrialized nation, and by the 1800s, London was the largest city in the world as a result of social changes brought about by this industrialization. Those changes included mass migration from the countryside into the city. Mass migration led to serious overcrowding issues. London quickly became a city overwhelmed by the waste products of its own population. The majority of this population lived in overcrowded slums where human waste piled up in courtyards and overflowed from basement cesspits into open gutters and waterways on the street. In such conditions, it was inevitable to see the rise of infectious disease, and outbreaks of disease such as typhoid and scarlet fever were very common in London in the 19th century. Cholera arrived in London in 1831 as an outbreak of a novel illness characterized by severe symptoms of diarrhea, vomiting, dehydration, and eventual death. This was an unfamiliar disease with frightening symptoms, an unknown mechanism of spread, and no cure. The 1831 outbreak was followed closely by epidemics of influenza in 1837 and typhoid in 1838. After these three epidemics, in 1842, Edwin Chadwick published The Sanitary Conditions of the Laboring Population, in which he used quantitative methods to show a direct link between poor living conditions, disease, and life expectancy. In this slide, we're looking at an example. This is a map from 1938 of the Bethnal Green parish or neighborhood of London. This map shows the mortality from 4 distinct disease classes. It overlays disease mortality with geographic location as well as employment, which is a proxy for living conditions or financial status. Chadwick used these integrated data to conclude there was a link between the living conditions of a person and the odds of contracting a disease. Edwin Chadwick's investigations inspired the Public Health Act of 1848 and the establishment of a General Board of Health, of which Chadwick was the first director. In addition to being the first director of the Board of Health, Chadwick was also the first Sanitary Commissioner of London. He advocated for the rapid removal of human waste as a way to quickly improve the health of the London population. In the course of his investigations into living conditions, Chadwick became convinced that active measures were needed, such as cleaning, drainage, and ventilation, and that these methods would improve the health of working people and therefore make them less dependent on welfare. So Chadwick advocated for the rapid removal of human waste, seeing it as a major source of the bad air that caused disease. We'll see more about this theory of disease spread in the next slide. Establishing this link between sanitation and life expectancy was an important revelation in how we track and predict infectious disease, even today. Unfortunately, although Edwin Chadwick advocated strongly for improved sanitation, he made only limited improvements to the sewage and drainage systems of the time, and those improvements actually led to a greater flow of raw sewage into the River Thames. This river was the main source of drinking water for London, and by further contaminating London's water supply, the risk of cholera was actually greatly increased. One of the underlying issues here is with the understanding of how infectious diseases like cholera are spread. The measures that Chadwick introduced were based on the medical thinking of the time, which attributed the spread of infectious diseases to foul-smelling air, called miasma. The miasma theory of disease was the prevailing explanation since the Middle Ages for how diseases spread. Briefly, it was thought that organic matter was operated upon by disease ferments that were present in the air during an epidemic, and that these ferments gave rise to disease. Supporting this theory was the horrible stench of decaying organic matter. Farr and Chadwick, and in fact most epidemiologists and public health officials at the time, adhered to this theory of disease spread. In contrast to miasma theory is the germ theory or contagion theory of disease, which holds that infectious agents are spread from person to person through direct contact. The germ theory of disease was established definitively by Louis Pasteur in 1865. However, cholera was impacting London several decades before Pasteur's experiments. There were two additional outbreaks in the mid-19th century of cholera in London, from 1848 to 49 and from 1853 to 1854, and these epidemics eventually led to greater than 20,000 deaths by 1855. The 1854 outbreak proved to be a pivotal moment in epidemiology. It is thought to have started on Broad Street in London, and pictured on this slide here is an illustration of the now famous Broad Street pump. We'll talk about what role the Broad Street pump played in the 1854 outbreak in a minute. Farr was by this time the leading authority on infectious disease and the premier epidemiologist of London. Farr concluded that cholera was spread via miasma, and Chadwick, the Sanitation Commissioner of London, agreed. Further, Farr also hypothesized that cholera was linked to elevation through what turned out to be a faulty analysis of the data of the time. A little-known anesthesiologist named John Snow had a different theory. At the end of the first cholera outbreak in 1849, London-based physician John Snow asserted that cholera was spread not by bad air, but by a waterborne contagion, and published a paper to this effect called On the Mode of Communication of Cholera. Now, Snow was not a member of the mainstream medical community. He was perhaps best known at the time for advocating the use of chloroform doses instead of the traditional method, which used a saturated cloth and then waited for the patient to pass out. As a result, Snow's communication on cholera was largely ignored by the medical community. After the second outbreak in 1854, Snow updated his paper with a statistical analysis of cholera deaths around Broad Street in the Soho district of London. In this slide, we see the famous spot map that shows deaths from cholera in the Golden Square area of London in 1854. The Broad Street pump that I mentioned a slide or two ago is shown with a red X on the map. Snow showed in his second analysis after the 1854 outbreak that the majority of cholera deaths were in homes around one particular public water pump, the Broad Street pump. He convinced officials to remove the pump handle to stop people from getting water from this source, convinced that they were picking up cholera from the water in that well. The handle remover happened as cholera was already on the downstroke, was already waning in London, and so removing the actual handle probably didn't do much to affect the course of the epidemic. However, based on these analyses, Snow postulated that a waterborne infection was the cause of cholera, and indeed it was discovered some years later that a leaking sewer ran very close to the Broad Street well, supporting a fecal-oral route of transmission that we now know is correct for cholera. Although the medical establishment could find no fault with Snow's analysis, they did not support his theory that it pointed to waterborne transmission for cholera. It's important to remember that the definitive confirmation of germ theory of disease, that disease is transmitted from person to person through a contagion, didn't come for another decade. John Snow is a pioneer in the field of what might be called analytical epidemiology, as a viable method for tracking infectious disease spread. Arguably one of his most important contributions is the concept of correlations and spurious correlations. Now, William Farr was a scientist, and he rightly recognized that the bills of mortality would be much more useful if they included more than just name and parish. Other information such as occupation, age, and actual disease. John Snow used William Farr's data to investigate correlations among them. For example, on this slide we see a table of the number and the odds of death from cholera among different occupations during the 1954 outbreak. These are based on data from the bills of mortality. Snow recognized the power of correlations, but also the peril. For example, if you look at the highest odds of death in the middle part of this table, you will see that egg merchants appear to have a very high odds of dying from cholera during this outbreak. However, John Snow rightly pointed out that this odds of death is complicated by the very small sample size. There weren't many egg merchants in their sample population. This statistical approach to data analysis, correlations, and identifying spurious correlations, as well as calculating risk, seems second nature to us today, but it was revolutionary in the 19th century. Snow, Farr, along with others like Edwin Chadwick, set the groundwork for widespread application of these concepts to infectious disease and other population-associated conditions. In 1866, London experienced one final cholera epidemic. By this time, John Snow had passed from a heart attack. In between the 1854 outbreak and 1866, an engineer named Joseph Bazalgette had redesigned Edwin Chadwick's narrow-bore sewers, which constantly overflowed and caused constant stench in the city. In Bazalgette's system, a series of large channels transported waste to be pumped into the Thames far downstream from London, where it washed out to the sea with the tide. As a result, there was far less contamination of the drinking water of London with human waste. Most of Bazalgette's new system was finished by the time 1866 rolled around, with the exception of certain areas in East London. William Farr analyzed mortality data from the 1866 outbreak and showed a very high concentration of mortality in communities served by the Old Ford Reservoir in East London. These affected communities with high mortality were almost exclusively communities that had not yet connected to Bazalgette's new sewage system. In light of these new data, William Farr subsequently supported John Snow's initial theory that cholera was caused by a waterborne transmission, and his analysis was considered conclusive to the medical community at large. Some of the lessons we've learned from this historical perspective. John Snow and William Farr were leaders, pioneers in the field. They were the earliest to use maps and records in combination, records of death, records of occupation, records of age, to track the spread of disease and ultimately try to identify its source and its mode of transmission. Today we have more powerful tools, including computers, including modern state-of-the-art laboratories, but we ask many of the same questions that John Snow and William Farr asked, including who is sick, what are their symptoms, when did they get sick, and where could they have been exposed to the infection. Finally, collecting the right data can be absolutely crucial in making valuable conclusions about an infection. Thanks to William Farr and John Snow, we have a much better idea of what data is useful in informing on the spread of particular disease. That's all for today. Thank you very much.